electronics, where he focused on the advanced semiconductor memory development. Igor is a Verasemi master inventor with greater than 80 patents to his names and has authored more than 15 IEEE papers. So with a round of applause, Igor Ovsosky. Thank you.
Thanks, Jack. Thank you, everybody. Thanks for giving me the opportunity to kind of take you through the material we prepared. As Chuck mentioned, I think a lot of this focus is going to be on the hardware side. I do provide an ample amount of introduction. As David, Chuck, and I discussed, I want to make this as informal as we can, so please stop me at any point. Ask me any questions. I'll try to do my best to answer them. I think Chuck kind of covered my one marketing slide on Avera. So you guys know what our company does. We're about 850 designers right now, mostly engineering company that's been doing ASICs for the past 25 years. Over 2,000 designs executed. And what we mean by ASIC, it's an application-specific integrated circuit. So think of it as a custom chip for a specific application. And as AI is becoming more and more prevalent, we are working with more and more AI customers to build these custom chips for these applications. So that was my marketing slide. I'll quickly jump to the outline of the talk. I'll start with just the artificial intelligence trajectory. This is just a fun slide that's kind of looking at the predictions made about how quickly AI will move in the next 50 years. Then I'll kind of jump on a couple of slides to kind of look at what AI is, artificial intelligence. How does it work? Cover some of the hardware trends that we're seeing in the industry, and then maybe jump into some other topics, such as comparing natural versus artificial intelligence, and then the societal impact that artificial intelligence might have. So let me start with just a fun slide on the AI trajectory. So this is a slide that kind of outlines some of the developments that were predicted by Ray Kurzweil. He's a Google fellow, a famous futurist that made these predictions in the 1990s, and so far he's batting about 83% accuracy. So on the leftmost slide, the leftmost portion of the slide, you can see 2019. These are some of the predictions that he made about computer wearables, about autonomous vehicles, AI, smart assistants like Siri, Alexa, Cortana, on-the-fly language translation. And although not all of these have come true, I think we're all working with some of these in our daily lives right now. In 10 years, the prediction is that Moore's law, which is the scaling, constant scaling in hardware performance, would produce computers that for $1,000 are 1,000 times more powerful than the human brain. Computers are going to be capable of autonomously learning and creating new knowledge. The brain mapping would have gotten us to the point where we can start replacing wearables with implantable devices, as scary as this might be to some of us. And then into the 2045, the prediction is that we would get to the point of singularity, where $1,000 can now buy a computer that is 1 billion times more intelligent than every human being on the planet. So this looks very, very steep as an advancement, and a lot of scientists would say that this is too fast. But we are seeing a pretty steep ramp in this field. About a couple of years ago, I was at a conference and we were predicting that this would be something that we would be working in 10 years, and it's already here. We're already building computer chips that are actually doing a number of these high-end tasks. So just a fun slide. So let me kind of go in through from the business aspect as well. Yeah, go ahead. Was there a question? Okay. On the business side, this is also a huge business opportunity. This shows the CAGR, the growth in this industry across the next 20 years here. And one thing that's kind of common is that this technology is being looked at as really technology that can change the world. The expectations by PricewaterhouseCoopers is that it would add about $16 trillion of worldwide GDP by 2030. So the potential is huge. These bar charts are kind of broken down in different colors, and they kind of show the different devices that would be making up that growth. So in purple are these application-specific devices that Avera specializes in, and then in the other colors you have some of the more known devices like CPUs, graphics processing units that are used in gaming platforms right now, and FPGAs, which are field programmable gate arrays. So the growth is pretty staggering here. And that's why you see a number of companies trying to get into this space. So what is AI? I'll start with just a very simple slide here. This is really a typical computer program. You have a function, you enter one variable, and you get an output. In a typical computer program, you would explicitly define the relationship between these variables, and you will deterministically execute every single time. So this would be a computer program that translates Celsius to Fahrenheit, for example. What you could do is you could actually do take a different approach and actually just collect a whole bunch of data that kind of links Celsius to Fahrenheit, and then create effectively an inductive programming, create a model that is kind of curved to that data. And in this case, this is a simple model. This is slightly more complex, and you can see there with more variables and more parameters, you can actually get a better fit. Or in some cases, if you add more and more parameters, you might actually get a worse fit. So there's some magic here that is actually happening between how these models are done, and there's a lot of machine learning scientists that are actually working this from the computer science side. Now, if you look at it, it's very simple. The simplest way to explain this is if you had a machine that's kind of shown here with lots of knobs, you have an input coming from the left, and in this case, these are different types of images. And on the right, you have some way of classifying these images. So it's either a car or a plane. And when you feed the images, you actually modify these weights in such a way that you can correctly identify a car or correctly identify a plane, and so on. So these weights, how you adjust these weights, which are the knobs in this machine, is really the key aspect of machine learning. How do you create a mapping function between the input and the output? And we have had machine learning with us for over 40 years right now. But usually we have attempted to do this modification in weights in a binary fashion. So it wasn't until the 80s or the 90s before we started to use what is called back propagation, which was the weights and the activations, which are the inputs, started becoming multi-bit as opposed to binary. And that allowed us to actually create gradients and actually train the machine to to recognize a specific pattern. So in this case, you can see the X input in the bottom of the slide, and the Y is the desired input. So the X input might be a picture of a car. The Y input might be the definition or the classification of that car. And then each of these stages will be different layers in the artificial intelligence system. And then at the end of the output, you would actually generate a difference between what you received and what was the desired output, and then use that difference or cost to actually feed it back and adjust each of the gradients for each of these layers. And by doing this many times, what you have is you've actually trained this deep neural network to actually recognize a specific pattern. Does that make sense so far?
Go ahead.
Okay. Yeah, please stop me if you guys, if I'm losing anybody along the way. If I look at a specific example of artificial intelligence, it would be a deep neural net used for image recognition. So the way this works is on the left side, you provide an image. On the right side, you get a classification of that image. And what you notice is that there's many different layers, and these are called neurons. They're really bio-inspired. Each of these green spheres is effectively an activation. And what happens is, in order to go from the one layer to the next layer, what you do is you actually multiply each activation by the weight along the edges of this graph. And when you add up all these activations that are multiplied by the weights, you generate the next layer here. And you do this operation again and again until you get to the classification layer. Now, what you notice is that as you go from the first layer, you initially detect edges. Then in the next layers, you detect features. You put these edges to detect features. These features are then combined until you actually have the classification layer, which is also called a fully connected layer. Lots of edges. Every edge is actually connected to every neurons in the previous layer. Very hardware demanding layer, but that's the layer that actually defines the classification. So what you notice here is that you see a lot of multiplication, because each activation needs to be multiplied with each of these edges, and then you have a lot of addition. Each of these results need to be added up together to generate the next layer activation. What you find is that from the actual hardware perspective, these devices are measured in teraops per second and teraops per watt. So what that means is that that is the amount of operations, either multiply or add, that they can execute in a second, and those are the multiply and adds that can execute in 1 watt of power. In other words, that's the energy efficiency of these devices. So you'll see these classifications every time you read about a specific neural network value. So if you continue the image recognition example, what you notice is that currently we're sitting at a point where the machine learning error rate is actually much lower than that of a human. The human error rate on a specific set of images is about 5%, versus machine learning is actually sitting at about 3% error rate. So machines have actually gotten better at recognizing images than humans can. And this started way back in 2010, where there was a bunch of software computer scientists that were actually trying to create programs to do image recognition. And this was done on a specific set of images called ImageNet. And for a while, these were done as conventional programs, the one that I described earlier. And then in 2015, I believe that's the time where we introduced neural nets, or deep neural nets, to actually do this training and classification. And at that point, we started improving to the point where now machines are better at recognizing images than humans are. So in a way, you can argue that we've already reached the singularity when it comes to just image recognition. Very focused, very narrow AI, but it's an example of what AI can do. And this artificial intelligence for image recognition has actually mapped into many different applications for deep learning. Medical image analysis is one of them. Self-driving cars is a big one. It's driving the industry really hard. Face recognition. Every time you upload an image on Facebook, for example, within 2 seconds, it passes through 7 different deep neural networks to determine who is in this image, whether the image is appropriate to be actually placed on Facebook, and so on. Language translation is another one that uses artificial intelligence, and then obviously security, diagnostics, and all kinds of other applications. Here, there's some examples of imaging type analysis where machine learning is getting to be very accurate in detecting anomalies, and in this case, I guess it's melanoma. So lots of interesting applications, and the list is continuously growing. So sorry, is there a question in the room? Okay. So, yeah, go ahead.
I noticed that one of the things that, with that New Zealand shooting, there was all kinds of videos, right, across Facebook and YouTube and the like. I'm assuming then they were using some sort of technology similar to this then to find them all, just take them down, because I can't imagine they had people sitting in the room watching every video at this point.
Yeah, exactly. So, yeah, if the sound is really bad, I think, from your mic, but I think I picked up what you were asking. You were saying whether Facebook actually uses this to detect videos that need to be taken down if they're inappropriate. Was that the question?
Pretty much. I guess I was referring, or specifically to that New Zealand shooting, because I mean they were taking down millions of videos within hours, or at least within the last day.
Absolutely, yeah. So this is there's a high level of automation of what's appropriate or not, but I think Facebook still has a layer of unfortunate group of human beings that actually has to review some of the images and the videos to finally take them off. So I think there's some automated level of scrutiny that's being done, and then it's escalated to a group of people that I think you can read articles on that have some serious mental problems with the job that they actually do. They see some really disturbing images, and they have to do this manually in some cases. But yeah, a lot of it is automated, and hopefully it gets to a point where it's all automated, so no human being needs to go through that. Yeah. Okay. Does that answer the question?
Yep. Thank you.
Yeah. Thanks. So just kind of go back to the hardware trends here. What I showed in the previous image is really this image detection, and what you notice there is a lot of multiplications in parallel and a lot of additions. And in the past, what we used to do is we used to use just normal CPUs to do this job. But what you notice is that CPUs typically have 2 cores, 4 cores, 8 cores, and so on, but it's still limited amount of compute. And although they're very flexible from the programmability perspective, they are really not the most optimized set of devices for implementation of machine learning. So the biggest workhorse right now in the industry is what they're called GPUs. So you can see NVIDIA, AMD, all these big companies are executing a lot of machine learning on these devices that have many, many cores on them, thousands of cores that can kind of in parallel do these multiplications and additions, so they can actually get a lot more work done, and they can get next level of efficiency. But as we kind of move forward and we have applications that are very specific, what we're seeing is that customers would go down the path of FPGAs, which are field programmable gate arrays, or really they're really programmable hardware. You can look at it in that way. Or if they have the resources and the money, they will go down the path of ASICs. If they have high volumes, they will design a custom device, something like the Google TPU that is actually targeted for a specific application. And by doing this, they can actually get significantly better teraops per second and teraops per watt. So they can get more compute power, and they can do that in a much more efficient way. So this is really the trend that we're seeing in the industry right now. So if you look at the hardware, though, it's still, when you compare it to the human brain, it's still very inefficient. The human brain is just so elegant when it comes to executing a lot of the compute. So what I've done here is I've attempted to do a comparison, and it's not really a fair comparison, but just looking at the human brain is actually being kind of labeled that it can actually do up to 10 petaflops per second of type of operation. And I've compared that to the number one supercomputer on the planet right now. That's about 200 petaflops. Now, yeah, it's a lot more compute power, but in the case of the supercomputer, it requires very distributed type loads that are really much you can execute them much more efficiently in a computer versus a human brain, which can actually do a lot of very connected type workloads. But just to do the comparison, you can see the memory capacity of a human brain versus this supercomputer that's the size of a football field. You can also see the power comparison, right? Human brain can actually execute a lot of this in using 20 watts versus the supercomputer burning 15 megawatts, basically. Needs a nuclear power plant just to supply the power to it. So you can see the efficiency there as well. So you can see from the hardware perspective, we're very far from actually getting to the biological inspired pattern recognition device here that we have on the left. So just a fun slide. So if you look at this, what are the challenges on the hardware side? What's making it inefficient? So what's making it efficient, you can look at, so this is the conventional compute or von Neumann or Neumann type computing. And the way it works is on the top here you have your memory. On the bottom you have your compute capability. So this is computing systolic array. So this would be like a Google TPU or an NVIDIA set of compute processors in the bottom, the portion of the slide. And the biggest problem here is there's a bottleneck of actually getting all this data from the memory into the compute region. So you have a lot of bandwidth inside the memory. So you can see the bandwidth capability here. It's hundreds of terabytes per second capability. Even at the memory I/O, you have over terabytes per second. But once you have to actually route all that data to the compute devices, you actually hit a bottleneck here. You have the system bus can only move hundreds of gigabytes, and then your compute can actually do a lot more, but you have a bottleneck right there. Now, if you look at this from another perspective, so this is the data bandwidth view. of the current computing. If you look at it from the energy consumption perspective as well, you can see the SRAMs themselves don't really consume that much power. They use up about 1.6 picojoules per bit. If you look at the network energy inside the cache, it's still pretty decent, 4.2 picojoules. But then if you look at just shipping this data across the device on the system bus, you're looking at 42 picojoules just to move that data. So you're not doing anything useful. You're actually moving this data back and forth. And again, if you compare this to something like a human brain, there's a lot of parallelism, and a lot of the memory and the compute are actually built into the neurons. So there's some level of inefficiency of us moving data from storage to compute and then back to storage. So what are the potential research opportunities on the hardware side, really? If you look at it, it's really just chasing these inefficiencies and trying to see what we can do to improve them, right? So one is really on the data movement side, right? So you have data transport makes up the largest energy cost associated with AI hardware. So the options are you figure out how to move less data, so get more efficient with your data that's moved, or improve the picojoule per bit moved. In other words, come up with different system bus architectures that are much more efficient, maybe low swing buses or encoded data or things like that to actually improve these components. Any questions so far?
No.
Okay. So one way to reduce the data is to go for this aggressive reduction in precision. So if we look at current devices, current training devices, what we'll notice is that they are all relying on floating point, a 32-bit floating point type activations and weights. So you can see the breakdown of that is 32 bits. You have a mantissa of about 23 bits, exponent of 8, and then you have a sign. So if you look at that, that's a huge amount of bits that needs to be moved from memory to compute and then execute the compute and then move back. So one way to improve this is to actually move to 16-bit floating point or 16-bit integer, or if not, move it even smaller to 8-bit. Now, you lose some accuracy in this mode, but there's a lot of research that basically shows that this can be done with very small loss of accuracy. So most of the training that's being currently designed is actually relying on a 16-bit floating point rather than the original 32. And then there's research from IBM and other places that's actually trying to push that down to the 88-bit. Now, this is on the training side, which really requires a lot more accurate representation of the data because you're still kind of setting those gradients. You're making sure that your devices are trained properly. On the inference side, and I'm introducing two labels here, training is something that's done in the data center. Inference is something that's deployed in the field. So these are the smaller devices that are in your cell phones. They're devices that potentially are going to be in your self-driving car and so on. Those don't require as much accuracy because the training has already been done on the data. Now you're kind of actually working with reduced data sets. And those we're currently using 8-bit integer or floating point, and those are slowly moving to 4-bit, and there's a push to get them down to binary type data. Now, we're still far from here. There's a lot of research, but nothing is really showing the promise on the accuracy that we're getting with 8-bit inference, but that is something that is basically direction that a lot of schools are heading down. So what the other benefit of actually doing this reduction in precision is the fact that on the memory side, you might need a significantly less memory usage. So by going from a 8-bit to a 4-bit, you actually get a quadratic reduction in area and energy as well. So there's a lot of benefit of actually doing these reduced precision calculations. Beyond reduced precision, again inspired by the human brain, what we notice is that although we have a lot of neurons in the human brain, and initially they're kind of not that well connected, and then as we age, they first have very high connectivity that ends up being pruned as we get older. What we're noticing is that not every neuron needs to be connected to every other neuron. What is being done in neural networks is actually to do something very similar, to actually go from fully connected networks and then prune specific edges and then do retraining to actually see whether that pruning of those specific edges resulted in any inaccuracy for that network. And if it doesn't, then you can argue you can reduce the amount of weight that you need to store in your system, and by doing that, reduce the amount of data that needs to be moved. Okay. Another opportunity for research is something that's very commonly seen at conferences, is the near or within memory computing. As I mentioned, memory, moving data from the memory to the compute and back into the memory is probably the most energy consuming part of AI. So there's a lot of focus to potentially bring the compute within the memories or near the memory, such that we don't need to shuttle this data for millimeters at a time across the device. So we can actually just bring it right next to the memory I/O or the memory sense amps, or even built it into the memory to actually get this improvement in energy. And if you look at the existing solutions here on the left, you can see the traditional computing. This is really the current CPUs. You have general purpose, it's accurate, it's robust, but it's really not efficient from the energy side. CPU and GPU would fall into this type of computing. A number of schools, universities are playing with analog in-memory computing. It's much higher energy efficiency, it's higher performance, but it does create a low precision, and it's susceptible to noise and PVT variation. So the way it works is, as opposed to you reading a conventional memory that's binary in nature, you would actually apply DAX at the word line, so you actually have different word line levels. That becomes your weights applications. You multiply that by the values at different memory cells that you can add up together, and then you interpret that data that's present on the bit lines with ADCs to convert them back to digital. I think this idea is really great on paper. I think the challenges are really variation. As we move to advanced node, SRAM device variation is really high, and I really have a hard time seeing how that maps into actual accurate deep neural networks. The last component that I like much more is the digital in-memory computing. So this is really bringing in the compute right next to the memory, but then still leveraging binary type performance within the memory to actually get both robust performance, but also get the benefits of actually bringing compute right next to memory. Any questions on this piece?
Nope.
Okay. Let me know if I'm going too far into the hardware side, and I'll try to emerge quickly then. Okay. So another way to bring memory into closer to compute is to actually pull in some of these DRAMs, which are heavily used in machine learning training applications, and pull them in closer and closer to the actual SoC. So on the left side here, what you can see is a silicon interposer. So it's effectively a silicon design that has wires on it and a very fine pitch. And what it is used, it's used to connect a SoC, which could be a GPU or an ASIC or a CPU, to a high bandwidth DRAM device. And you can see this DRAM device is actually multiple stacks of DRAM that are basically that are feeding large capacity memory, and they're providing low power, high bandwidth access of that memory to the CPU or the GPU. So this is what's currently used on a number of GPUs or a number of TPUs in the industry. And the benefit of this is really just memory bandwidth, increased memory bandwidth, which is something that's always needed for AI applications, and then better efficiency because you're moving this memory bandwidth over a couple of centimeters rather than moving it multiple inches on a PCB. The next generation of this, however, is to actually move this DRAM stack and bring it closer and closer to the logic, to the compute. So ideally, what we can do is we can actually stack these DRAM devices on top of a SoC and improve both the efficiency and the bandwidth with which we can move that data from the DRAM into the SoC. That comes at the cost of thermal challenges. So now you're putting DRAM, which is really sensitive when it comes to temperature, you're putting it right on top of a logic die, which is doing a lot of compute, and it can heat up pretty quickly. So a number of exotic cooling solutions are being introduced, especially in the supercomputer. There's thousands of dollars being spent just on the cooling solutions alone, just to actually be able to cool this DRAM efficiently. So that's another interesting approach moving forward. Okay. And then the summary on the hardware learning piece, really deep learning acceleration has strong dependence on memory, as I mentioned. We need to figure out how to feed these massive parallel engines, and we need to do that in a very efficient way. On-chip memory needs to improve, so any improvements in megabits per millimeter squared of memory that we can put on chip, or 3D integration, kind of like what I mentioned with the HBM, stacking memory above to actually kind of improve bandwidth and reduce the power associated with it. And then beyond that, we'll still need reduced precision and sparsity of the matrix to actually, I need to leverage that to maximize efficiency. And if we look at beyond that, there's obviously all these interesting heterogeneous integration ideas, emerging memories like MRAM and RRAM and so on that promise higher densities or allow in-memory computing in a more efficient way. And different architectures are constantly being explored here. So that kind of covers the hardware piece. In the next couple of minutes here, I wanted to also maybe touch on briefly on the societal impacts of AI. If you look at AI, we're kind of compare the human brain with AI systems. We're really dealing about 100 billion neurons. Each of them fire at a very slow speed, about 200 hertz. The axon transmission rate is about 100 meters per second, so it's not really fast, not that fast. And then if you look at all of that, it's kind of limited by the brain size. In other words, you can only put so many neurons in that area. Now, there's also a lot of tricks that we still don't understand about the human brain. But if you look at AI systems on the other side, right now they're there's less transistors per chip, but they are growing with Moore's law. Despite the fact that there's a slowdown in Moore's law, there's also all these heterogeneous type integrations that are kind of expanding or continuing the scaling. Transistors switch at about 10 gigahertz, so 10 billion times a second. Electrical interconnect is close to the speed of light. Computer size could be football fields. And both hardware and software are evolving fast. So if you look at artificial intelligence, I think it's moving at a fast pace, and it doesn't really have a limit that it needs to stop. So I think we can quickly go from look, the cute robot can do tricks to open the pod Baydar, from the 2000 Odyssey. So this is a challenge that needs to be looked at, and I know general AI still seems far, but I think beyond just electrical and computer engineering, I think we need to really couple our field with a lot of look into policy and philosophy of how we're going to handle this technology. I've kind of looked at some of the potential benefits of AI. We can consider, as humans, we can consider 7 thoughts at a time, versus AI can actually evaluate thousands of parameters and petabytes of data for making a decision. And if we use it for good, we really could improve society. If you look at just self-driving cars, they're expected to save about 1.3 million people from car accidents worldwide. Cancer detection is actually something that it's using AI today. Who knows, in the future we might have a cure for cancer. And really has the ability to improve the standard of living. If you couple renewable energy with really tireless AI, constant improvements, we could all have a great life. If you just look at the finances at the bottom of the slide, kind of, they do show a huge value that could be brought to the world. The question is how is this going to be distributed across the human population here? It has a lot of risks as well, and they're worth mentioning. Privacy is becoming a big challenge. If we look at a number of countries in the world that are investing very heavily on security cameras that can effectively detect and label humans within seconds, so you can actually detect every human in your entire country by face recognition within seconds. Racial bias is already surfacing in some recognition systems. We have chatbots like Tay from Microsoft that, after being released in the cyberspace, have been sort of quickly converted into neo-Nazi sex bots just by chatting with the select part of our population. There's also impact on democracy. We're kind of focusing more and more power in fewer hands. In the past, supervisors could give directions and employees can decide to disagree, which was inefficient and imperfect, but you still have safeguard there. In the future, you can argue that supervisor gives the directions and robots execute that without question. So lots of challenges. Arms race, inequality are some of the big ones that I see as well. So these are a couple of fun slides that I grabbed from TED, and they were kind of showing which jobs would be impacted the worst by AI. So I think the x-axis here is creativity. On the right side, optimization on the left side, and then the y-axis is compassion needed or compassion not needed on the y-axis. So you can see a number of titles, and just to be fair, the guy that was presenting this slide was a CEO, so he placed the CEO in the top right corner there. So it wasn't my slide, but what his message was that a lot of these jobs might be fully replaced by AI. So the bottom left corner, stuff that requires optimization, but it doesn't really need compassion, would be fully replaced by AI. On the compassion needed, but optimization needed, you can argue AI would be working together with humans. Same with the top right quadrant, and then you see a slow transition of AI covering more and more human plus AI in the bottom right uh, quadrant here. So yeah, I think this is going to have a significant impact on how we organize our society, and it's worth kind of pursuing before it gets there. Um, I think that's all I had. I'm going to leave you with one slide here. And again, this is also another TED Talk that I kind of grabbed. I had to do this presentation for the Vermont State House as they're kind of trying to align on their strategy to deal with AI. And that this slide kind of seemed appropriate. On the left side, we have human inventions like fire and cars, where we could learn from our mistake. You get burned, or you have people that get hurt without seat belts, and you kind of correct it. On the right side, we have these technologies that are kind of significantly more impactful, and we really need to get them right the first time around. Nuclear power, synthetic biology, artificial intelligence. There's an interesting website and a group that I'm a part of that actually looks at what are some of the laws and what are some of the policies that need to be placed in to kind of get ready to meet the changing ecosystem here as AI becomes more prevalent. So that's all I had. There's a lot of noise, so I hope I didn't talk through lots of questions, but maybe I'll stop right now and try to answer any questions that you might have had.
Okay, so for the people sitting in the back seat, Dave has a handheld mic. For those who are sitting in the front, I believe that Dave has turned on the mic, so you can actually talk directly into it. Got any question for Igor? We have one.
Yes, a question here. What is your level of concern of, you talked about HAL 9000, I mean, kind of taking over, or the AI machine becoming self-aware? I mean, is that, have you thought about that?
Yeah, so I think you'll hear probably many differing opinions. This slide is probably the right slide to look at it. If you look at the slide, they've actually interviewed about 100 of top AI experts in the world. So they've picked the top 100, and they've asked them what is their probability that they give to the rise of the singularity, and by which year. And what they found is that by 2045, 50% of them agree that the singularity would be happening by that day. So in other words, 50% of them say it might be before that, 50% might be after it. This is the median age that they're basically predicting that the singularity would arise. Now, if you look at hardware, a lot of the hardware experts are going to tell you, look, Moore's law is slowing down. There's a lot of challenges, but we've been, in my opinion, we've been in this boat many times before, where we have kind of said scaling is dead. We're not going to find a way forward, and yet we have. There's always been new developments that have kind of allowed us to kind of keep moving. So I think it's definitely something that we need to be discussing, and a lot of people might be concerned about the singularity. I'm actually concerned more about the developments that are happening within before that. In other words, surveillance and these electronic dictatorships that are slowly arising in different countries around the world. I think those could have a very negative impact as we kind of move forward, and I think we need a global approach to dealing with them, which is really hard to do lately. Yeah. Hope that answers your question.
Just want to add on what Igor said. So I think CNN reporter did an experiment trying to act suspiciously in front of a camera in China, and he was caught within 3.5 minutes after he did that.
Yeah.
So
Yep.
the goal right now for the public safety in China is they want to build a database of who you are, what you're doing, and what you will be doing. Sounds kind of like futuristic, but that's the direction the AI is heading to right now in China.
Yeah, and a lot of people can look at that as a fantastic way to deal with terrorism and other things. But we also need to also look at the other side of that, which is really privacy of its citizens and the ability to express dissent. It's kind of disappearing with the fact that, like Chuck said, within 3 minutes you could be picked up just by acting strange. Yeah. So yeah, those are key concerns, I think, as this technology arises, because it's not something that is futuristic. It's actually already out. I think the police in China have the ability to actually wear these glasses now, and we've been in these giant train stations through China where police officers wearing these glasses can actually identify citizens within 3 seconds. They can actually get all the information just by looking at a specific person. So think about a billion people in China and figure out who that is within 3 seconds just by looking at them.
Igor, we have another question from the audience.
I have a question. There's been a lot of focus on when everything is working right. Has there been any looking at what happens if a sensor fails or something? And it's coming to light now with the Boeing situation where artificial intelligence makes bad decisions because of bad input?
Yeah. Yeah, so that's a great question. I don't know if the Boeing specific problem is an artificial intelligence implementation of something. I would doubt that, but I think you bring up a very good point on the diagnostics phase, because as I mentioned earlier, a lot of the computer programs and a lot of the solutions are probabilistic in nature. They're not exact the way a typical computer program will be done. They would be an approximation of some sort for a specific application, right? So if, for example, I chose to curve fit this set of data with a different order, I overfit it. Who knows if I end up in a problem having some type of a problem that is basically being predicted over here in the curve rather than where the curve actually wanted to go. So that is a big challenge, I think, trying to make sure that something is deterministic in nature. And what you'll see is that a lot of these, especially on the automotive side, you will see companies training on a specific set of data and then trying to present adversarial type images that are there's a lot of noise on them, or there's a different ways to actually try to fool the system to try to make them more bulletproof. But in a way, they are probabilistic in nature, all of the AI systems.
Kind of add on to that. So Igor, about 2 years ago, Igor was leading a Verasemi discussion of a very prominent car manufacturer in this country. And there were a lot of requirements imposed on what they want to do for ADAS, which is kind of a assist driving chip they want to put in their car. One thing that kind of stand out in my mind is they want to do BIST. They want to be able to do in-system BIST live every few seconds to make sure the chip is operating and there's no defect. So there's a lot of safeguard that engineers want to put in to ensure the safety of the system, safety of the passenger, not the system. And a lot of redundancy are built in there. Engineers will always do the best they can, but
Yeah, that's a great point. I mean, a lot of the systems are going to be verified in the hardware, and then there's also going to be competing systems. So, in the case of automotive, there's been discussions where a customer would actually use multiple chips from multiple vendors just to make sure that they all agree with the decision that the car is going to make. So, in other words, you have almost like voting algorithms where you have like three separate chips that are all making a decision, and if they all align in the decision, the car takes that path. And if it doesn't, the car is put into a safe mode and maybe pulled off the side of the road until it's determined what went wrong. So there is a lot of systems in place, but they are still probabilistic type solutions, which is the way our human brain works as well. So it's, yeah, you can't argue that we are 100% deterministics when we drive our car, especially when the kids are going crazy in the back.
Maybe we have time for one more question. It's kind of getting late in Burlington. Sorry. Do we have any other question? Well, if not, maybe we should let Igor go. Thank you so much, Igor, for talking to us today. Has been a great talk. If you have any question afterward, please feel free to reach out to IEEE to reply back to the email address, or you can, Dave has my contact information. I can make sure this gets to Igor. It's a very exciting field. I mean, we here in Rochester, and we just taped out an AI chip, a massive AI chip. We probably broke the radical on that one, it's a 14 nanometer one. But it's really exciting. Like what Igor said, there's a lot of growth potential. We want to do what's right. So if there's not if there's nothing else, a round of applause for Igor. Thank you very much. Thank you.
Thanks, everyone. Thank you.
Yep. Thanks, Igor. And then just one more. Let's see. We can let Igor log off.